Now coming to the different types of mitigation techniques. In the channel fading, in order to avoid the channel fading in the communication, we are supposed to use several mitigation techniques. In that, a list of combating the effect of both signal to distortion and loss in SNR. The figure can serve as a guide to indicate which technique is best suited for the degradation due to various fading effects. The mitigation approaches to be used when designing a system should be considering of two basic steps. The first one, choose the type of mitigation to reduce or remove any distortion or degradation. Second one, choose the diversity type that can be best approach AWGN system performance. Once again, I repeat, in order to remove the fading effect in the channel, we are supposed to use two basic mitigations. In that first one, choose the type of mitigation to reduce or remove any distortion, degradation. And the second one, choose a diversity type that can be best approach AWGN performance. Now, coming to the different types of combat methods to avoid the distortion with respect to fading. First one to combat of distortion, second one to combat of loss in SNR. In order to remove the distortion with respect to frequency selective, we are supposed to use adaptive equalization. In the adaptive equalization, decision feedback and the variable equalizer are supposed to use. And the second one, spread spectrum. In the spread spectrum, we are supposed to use direct spread spectrum or frequency hopping spread spectrum. We'll learn in future videos. And third one is orthogonally FTM. Next one is the pilot signal. It is methods to avoid frequency selective distortion. And coming to the fast fading distortion. Why? Because fading is nothing but a distortion. In order to avoid the fast fading distortion, we are supposed to use robust modulation type, signaling redundancy to increase the signaling rate, and third one, coding and interleaving. So coding and interleaving is the one of the important topic in the information theory. And to combat loss in SNR, in order to avoid the flat fading and the slow fading, we are supposed to use some type of diversity to get additional uncorrelated estimated of signals. And the second one is error correction codes. By using of these two steps, we eliminate flat fading and slow fading in the channel. And coming to the diversity types, in order to combat loss in SNR, we are supposed to use diversity types. The diversity types based upon time called as interleaving. Diversity based upon the frequency comes under bandwidth expansion, spread spectrum FH and DS with a rack receiver. Already we explained in the previous video. And next one is the spatial, nothing but space received antennas. And next one is the polarization. Here the important point is polarization. Basically in communication, in electromagnetic communication, we are supposed to use three types of polarizations. One is linear, second one is circular, third one is elliptical. The process of linear again is consisting of two methods. One is the vertical polarization, second one is the horizontal polarization. And the magnitude of electrical field and magnetic field intensity with the same intensity base with respect to x and y axis, it comes under circular polarization. If it is not equal, it comes under elliptical polarization. So the type of polarization is totally dependent upon the type of antenna which we are using in the transmitter side as well as the receiver side. So by using these type of methods, we are avoid frequency selective distortion, fast fading distortion, fast fading and slow fading distortion, and etc., which can occur in the channel. And move to the next step, mitigation, the degradation effects of the fading. What are the mitigating steps we have to consider? In the below figure, we highlight three major performance categories in terms of bit error probability, that is PB, next versus EB by N naught. The leftmost exponentially shaped curve highlights the performance that can be expected when using any nominal modulation schemes in AWGN interface. Like any nominal modulation schemes depend upon either analog or any digital. Observe that at any reasonable EB by N naught level, good performance can be expected. The middle curve referred as a relay limit shown the performance degradation resulting from the loss in EB by N naught, that is characteristics of flat fading and slow fading when there is no line of sight signal component present, when they with that out of line of sight, that means out of line of sight. The curve is a function of the reciprocal of EB by N naught. So far, practical values of EB by N naught performance is generally be a bad. Now, in case of relay fading, parameters with overpass are often introduced to indicate that an average is being taken over a ups and downs of a fading experience. Therefore, one often sees such a bit error probability plots with the average parameters denoted by EB by N naught and probability error. These notations are emphasize the fact channel has memory, thus received samples of the signals are correlated to one another in time. Therefore, when producing each probability error plots for a fading channel, no needs to examine the process over a window of a time that much larger than channel coherence time. The curve that reaches an irreducible error rate level, sometimes called as error floor, represent awful performance, whereas bit error probability can level up to nearly 0.5. This shows the several performance degrading effects that are possibly with a frequency selective fading or fast fading. Mitigating the degradation effects of fading channels, if the channels introduce a signal to noise ratio as a resultant of fading, the system performance can exhibit an irreducible error rate at a level higher than the desired error rate. In case of no amount of EB by N naught will help to achieve the desired level of performance, and the only approach available for the improving performance is used to some form of mitigation to remove or reduce the signal distortion. The mitigation depends on whether the distortion is caused by frequency selective fading or fast fading. Once the signal distortion has been mitigated, the probability error versus EB by N naught performance can transition from awful category to bad relay limit curve. Next, it is possible to further emulate the effects of fading and straight approach to AWGN system performance by using some form of diversity to provide the receiver with a collection of uncorrelated replicates of signals by using powerful error correction codes, but it is somewhat difficult to manage and it is somewhat difficult to remove the fading effect in the channel. It needs a more number of algorithm, more complex need of algorithm to run to remove the channel fading effect in the receiver side. Now we observe the plot variations of EB by N naught with respect to probability of error by considering three types of distortions. One is AWGN, that is A2 white Gaussian noise. Second one is flat fading, and third one is frequency selective fading. Now we can observe that the variation of probability of error which comes under moves 0 to 35. Let us consider the probability, the EB by N naught value is approximately equal to 5. At a 5 value of dB, a 5 dB of EB by N naught, the AWGN channel approximately equal to 1 by 10 to the power of minus 2, that is 1 by 100, that is a 0.001. At the same value, the flat fading will result, that is 1 by 10, that is 0.1. At the same value, the frequency fading will result equal to 1. In the first case, we approach 0.01 probability error. In the second case, we approach 0.1 probability error. And third case, the probability error equal to 1. Now, we have to decide which type of a channel we are supposed to use to remove the fading in the channel. In all the cases, AWGN channel will lead a lower value of a PB when compared with the flat fading and frequency selective fading. Now we are moved to the different types of mitigations combat to channel fading. Now, equalization can mitigate the effects of channel induced ISI, that is brought on frequency selective fading. That is, it can help to modify the system performance degraded the curve is awful to one of the merely bad. The process of equalization for mitigating ISI effects involves using the method to gather displayed symbols energy back into original time interval. The effect and equalizer is inverse filter of the channel. If the channel is the frequency selective, the equalizer enhances the frequency components with small amplitude and attenuate those with large amplitudes. The goal is for combination of the channel and equalizer filters to provide flat composite received frequency responses and linear phase, because in a mobile system the channel response varies with respect to time. The equalizer filter must also change or adapt to the time varying channel characteristics. Such equalizer filters are therefore adaptive devices that accomplish more than distortion mitigations. They also provide diversity, since distortion mitigations is achieved by gathering the dissipated symbols energy back into the symbol's original time interval. So that is not a hamper the detection of other symbols. The equalization is simultaneously providing the receiver with a symbol energy that would be otherwise be lost. In the mitigation to combat of frequency selective distortion, we are supposed to use an equalizer that is called a decision feedback equalizer. Already we expressed in the above figure. The decision feedback equalizer has a feed forward direction that has linear transversive filter whose stage, length and tap weight values are selected to coherent combined virtual all of the current symbols energy. The DFE also has a feedback section which removes energy remaining from the previously detected symbols. The basic idea of the DFE is that once an information symbol has been detected, the inter-symbol interference that has induced on future symbols can be estimated and subtracted before the detection of subsequent symbols. And the method number 2, the maximum likelihood sequence estimation equalizer. It is the second category of equalizer. It tests all possible data sequence rather than detecting of each received symbol by itself, and choose the data sequence that is most probable of all candidates. The MLSE equalizer was first proposed by Forney and implemented by using of Viterbi decoding algorithm. The MLSE is an optimal in the sense of that is minimizing the probability of sequence error, because the Viterbi decoding algorithm is typically used in the implementation of MLSE equalizer. The device is often referred to be a Viterbi equalizer. Later, we go for global system for mobile communications using Viterbi equalizer. There is a place of Viterbi equalizer in global system mobile communications plays a crucial role. And category number 3, direct sequence spread spectrum technique. It is also comes under mitigation with respect to frequency. It can be used to mitigate the frequency selective distortion because the hallmark spread spectrum sequence hallmark spread spectrum systems is there capable to reject interference, and ISI is the type of interference. Consider a DS by SS direct sequence spread spectrum binary phase shift key communication channel comprising one direct path and one refracted path. Assume that the propagation from the transmitting to receiver results in a multipath wave that is delayed by tau compared with the direct wave. Neglecting the noise and the receiver signal can be expressed in terms of R of t is put in the equation 15.35. In the above equation of R of t, x of t is the data signal, p of t is the pseudo-random spread growth, and tau is the differential time delay between two paths. The angle of theta is a random phase as summed to be uniformly distributed in the range of 0 to 2 pi. And alpha is the attenuation of multipath signal relatively to the direct path signal. The receiver multiplies the incoming R of t and the code P of t. If the receiver signal is synchronizing to the direct path signal, multiplication can be done code signals else. It will be represented as R of t is multiplied by the P of t. It is shown in the equation 15.36. In the equation of 15.36, P square of t is equal to 1. If tau is greater than the P and chip duration, then integrating of a P of t into P of t minus tau dt must be less than integration of P square of t into dt. To overcome appropriate interval of integration like correlation, the spread spectrum sequence efficiently eliminates the multi-part interference by virtue of its code correlated receiver. Even though the channel induced ISI is typically transparent to spread spectrum systems. Such systems suffer from the loss in energy contained the multipath components rejected by the receiver. The need of gathering up this lot of energy, such a multipath chips, was motivation for developing of Rake receiver. The Rake receiver dedicates separate correlation to each multipath components and coherently add energy from the each finger by selective delaying of each. So they can all coherently combine by using of a rake filter which is using in the channel receiver side. Earlier we described the channel that could be classified as a flat fade, but occasionally exhibits the frequency selective distortion when the null of the channel's frequency transfer functions occurred at the center of the signal band. The use of direct spread spectrum sequence is a practical way of mitigating such distortions because the wideband spread spectrum signals can span many lobes of the selecting fading channels in frequency responses. Hence, a great deal pulse energy is passed by scatter medium to construct the channel null effects on relatively narrow band signal. The ability of signal spectrum to span over a many lobes of a frequency selective transfer function as a key to how direct sequence spread spectrum signaling can overcome the degradation effects of multipath environment. This requirement that spread spectrum bandwidth and greater than the coherent bandwidth F0. The ratio of W and F0, W means spread spectrum bandwidth and F0 means coherence bandwidth, are more effective will be the mitigation. The time domain view of such a mitigations are expressed in the above equations that resolve the multipath components. And it required the spread spectrum signal dispersion to be greater than a chip time. Now, one more frequency mitigation that can be done by frequency hopping spectrum. Frequency hopping spectrum can be used as technique to mitigate the distortion caused by frequency selective fading. Provide the hopping rate at least equal to the symbol rate. Compared with the direct spectrum sequence mitigation takes place the different mechanism. FH systems avoid the degradation effects due to multipart by rapidly changing the carrier frequency band in the transmitter. In interference is avoided by similarly by changing the band position in the receiver before the arrival of multipath signal. So it happened in the frequency hopping spectrum. So maximum of receivers are supposed to use FHSS as the one of the efficient method to remove frequency selective fading. And last but not least, that is orthogonal frequency division multiplexing. So we can be called as OFDM. OFDM can be used for signal transmission in a frequency selective fading to avoid an equalizer by lengthening the symbol duration. The approach is to partition a higher symbol rate equivalence into n symbol groups so that each group contains a sequence a lower symbol rate by factor of 1 by n than the original sequence. A signal bands made up of n orthogonal carriers waves and each one is modulated by different symboling group. The goals to be reduce symboling rate, that is W is approximately equal to 1 by T. Each of carrier such that it is less than the channel coherence bandwidth F0. Orthogonal frequency division multiplexing, originally referred to a kineplex, is a technique that can be implemented in United States in mobile radio systems and has been chosen by the European community. Under the same coded OFDM, the high definition televisions broadcasting are supposed to use. Now it is plays an important role in MIMO systems as well as in massive MIMO systems. By using orthogonal frequency multiplexing process in the channel, in the receiver, and the channel and the transmitter, we supposed to use MIMO and massive MIMO system developments. And the last one is pilot signal. Pilot signal is a name given to the signal intent to facilitate the coherent detection of waveforms. Pilot signals can be implemented in the frequency domain as in band tones, or they can be implemented in the time domain as a digital sequence, which can provide the information about the channel state, thus improve the performance of fading conditions. So these are the methods we are supposed to use mitigation to combat the frequency selective distortion. Once again I repeat, the mitigation combat frequency selective distortion can be fulfilled by the decision feedback equalizer and the maximum likelihood sequence estimator and direct frequency spectrum technique, and next one is frequency hopping spectrum technique, and last one is the OFDM, and next one is the pilot signal. Each method having its own importance to reduce the fading that can be formed by the frequency. Hope that maximum of research is going on in this part by using OFDM. So sure that OFDM is an important multiplexing technique to avoid frequency fading in the channel. So that's why there is a lot of research scope in orthogonal frequency division multiplexing using in the transmitter side as well as in the receiver side. Now we are moved to the next part, that is mitigation to combat fast fading distortion. Fast fading distortion calls to use robust modulation scheme that not required any phase tracking and then reduce the detector integrator time. Another technique is to increase the symboling rate, that is W is equal to 1 by Ts, such that it is greater than the fading of Fd is equal to 1 by T naught by adding signal redundancy. Error correction codes can also providing mitigation. Instead of providing the more signal energy, a code reduce the required EB by N naught for desired error performance. For a given EB by N naught with coding present, the error floor of the demodulator will not be lower, but lower error rate out of the decoder can be achieved. Thus, with coding, one can get acceptable error performance and in effects withstand with the large error flow from the demodulator that might have otherwise been unacceptable. To realize these conditions of benefits, error of errors out of the demodulator should be uncorrelated, which will generally to be case of fast fading environment, or interleaver must be incorporated into the system design. Due to that, complexities goes on increases. An interesting filter techniques can be provided to mitigating for fast fading distortion and frequency selective distortion. The frequency selective distortion can be mitigated by using OFDM signal step. Fast fading, however, the typically degradation convention of OFDM because of Doppler spread corrupting and orthogonal frequency of OFDM subcarriers. A polyphase filter technique is also used to provide time domain shaping and partially response fading. In order to reduce spectral sidebands of the signal, thus helps to provide a orthogonality. The process introduced to known as ISI and adjacent channel interference, which are then removed by the post processing equalizers and cancelling filters. In the next topic, mitigation to combat loss in SNR. After implementing some of the mitigation techniques to combat the signal distortion due to frequency selecting or fast fading, the next step is to use diversity methods to move the system operating point from the error performance curve labeled as bad to a curve to approach the AWGN performance. The term of diversity is used to denote the various methods available for providing the receiver with uncorrelated reductions of the signal of interest. Uncorrelated is the important feature here, since it would be help to receive to have additional copies of the signal if the copies were equally pure. Following are some of the ways of which diversity methods can be implemented. In the first one, the diversity method based on time called time diversity. Time diversity can provide by transmitting a signal on L different time slots. Once again I repeat, time diversity can provide the transmitting signal on L different time slot with a time separation at least T naught. When used along with the error correction codes in form of time diversity. That means in between every time interval we are supposed to add an error correction code to form a time diversity approach. It is the one of the best approach method as used in GSM technology. And the second one is frequency diversity. Frequency diversity can provide a transmitting of L different carrier frequency separations at least by F0. Bandwidth expansion is a form of operating diversity. The signal bandwidth W is expanded so that it is greater than F0, thus providing the receiver with several independently fading signals replicas. These achievable frequencies of order L is equal to W by F0. When the signal W is made larger than the F0, there is a potential of frequency selective distortion unless mitigation form of equalization is provided. Thus, an expanded bandwidth can improve the system performance only if the frequency selective distortion that diversity may be introduced into mitigated. And the next one is frequency spectrum systems. The frequency spectrum systems are excel the rejection of interference signal by use of bandwidth expansion techniques. In case of DSS, it was demonstrated earlier in the multipath. Components are rejected if they are time delayed by more than duration of one chip. However, in order to approach AWGN performance, it is necessary to compensate for the loss in the energy contained in those rejected components. We discussed in the previous the rake receiver. The rake receiver makes the possible coherent combine the energy form of a several of multipath components arriving along the different paths. Thus, use the rake receiver in DS and SS modulation can be set achievable path diversity. The rake receiver is needed to phase coherent reception, but differentially coherent Budbee detection and simple delay equivalent to the duration of 1 bit with complex conjugate can be implemented. And next we are moved to frequency hopping spectrum. Sometimes used as a diversity mechanism, the GSM systems use slow FH nearly 217 hops per second to compensate for those cases where the mobile unit moving very slowly and experiencing deep fading due to the spectral null. And the next one is spatial diversity. Spatial diversity is the useful accomplished through use multiple receiver and antennas separated by distance at least 10 wavelengths when located at the base station. Signal processing techniques must be employed to use a best antenna output or coherently combine all the outputs. Systems have also been implemented with multiple transmitters, each different location, as in the global position system. It can be called as a GPS. And the last one, that is polarization diversity. Another way to achieve additional uncorrelated samples of the signal. Any diversity scheme may be viewed as a trivial form of repetition coding as a space or a time. However, the techniques must be improve the loss in SNR in a fading channel that are more efficient and more powerful than the receiving coding. Error correction codes present as unique mitigation technique because instead of providing more signal energy, it reduces EB by N0, need to achieve desired performance level. Error coding compound with the interleaving is probably the most prevalent of mitigation scheme used to provide improved system performance in a fading environment. Note that the time diversity mechanism obtained through interleaving relays on the vehicle motion to spread the error during the fading. The faster the speed of mobile unit is, the more effective is the interleaver. The interleaver is less effective than the low speed. That is, the vehicle speed versus interleaving performance is demonstrated in the next videos. And the next one is diversity techniques. It is the last one to remove the frequency selective fading methodology. The goal in implementing of diversity techniques to utilize additional independent signal paths to improve the received SNR. Diversity provides improve the system performance at relatively low cost, unlike equalization. Diversity requires no training overhead. In this section, we show the error performance improving that can be obtained with using of diversity techniques, the probability error PB and average through all up and downs of fading experience, and the slow fading channel can be computed. The PB of a slow fading channel computed is given by integral 0 to infinite PB of x multiplied by P of x into dx, where PB of x is the probability error for a given modulation scheme at a specific value of SNR x, where x is equal to alpha square EB by N naught, and the P of x is the probability distribution function of x due to the fading conditions. With EB and N naught constant, alpha is used to represent amplitude variations due to the fading. For a relay fading, alpha has relay distributions, so alpha square and consequently of x have a chi-square distribution. The following the form of equations P of x is equal to 1 by tau exponential of minus x by tau for x must be greater than or equal to 0. In the above expression, tau is equal to alpha square multiplied by EB by N naught is the SNR average through up and downs or fading. If each divestry branch for I equal to 1 to m, the instantaneous SNR of gamma, and we assume that each branch has same SNR given the value of tau, then P of gamma I is approximately equal to 1 by tau into exponential of minus gamma I by tau, where x is replaced by gamma I. For gamma I must be greater than or equal to 0. Then the probability of single branches of SNR less than the some threshold value of gamma, that is P of gamma I must be less than the gamma, is equal to integral 0 to gamma P of gamma I into d of gamma, that is equal to integral 0 to gamma 1 by gamma into exponential of e to the power of gamma I by tau into d of gamma I. This is approximately equal to 1 minus exponential of minus gamma I tau I, that is 1 minus expected probability. The probability of all m independent signals in the diversity branches are received simultaneously with SNR less than some threshold value of gamma. That is, the P of range from starting from gamma 1 to gamma, which is approximately equal to 1 minus exponential of e to the power exponential of minus gamma I tau whole power of m. The probability of any signal branch achieves SNR greater than gamma, that is P of gamma I greater than gamma, that is equal to 1 minus the above expression, that is 1 minus exponential of e to the power gamma exponential of gamma by tau whole power of m. So this is the probability of exceeding threshold when the selection diversity used. So it is one of the best diversity techniques to estimate the probability of error based upon the thresholding concept. Let us consider an example. A 4-branch diversity is used and that each branch received an independently relay fading channel. If the receiver SNR at tau is equal to 20 dB, determine the probability that all 4 branches and received simultaneously with SNR less than 10 dB. Compare the results with no diversity applied scheme is used. So again I repeat the question. Assume that 4-branch diversity is used and that each branch received an independent relay fading signal. If the average SNR is tau is equal to 20 dB, determine the probability of all 4 branches are received simultaneously with an SNR less than 10 dB, and also compare these results with no diversity applied scheme is used. In the above solution, we are supposed to use the equation which was discussed in the 15.42. In that, gamma is equal to 10 dB and gamma by tau is equal to 10 dB minus 20 dB, that is approximately equal to minus 10 dB, that is 0.1. We solve the probability of SNR will drop the less than 10 dB, that is given in the problem. Based on the condition, the probability of gamma 1, gamma 2, gamma 3 and gamma 4, why? Because there is a 4 branches, so that's why we need to consider gamma 1, gamma 2, gamma 3 and gamma 4. If it is 5 branches, consider gamma 5. If it is n branches, consider gamma n. But as a problem, they will give only 4 branches, that means gamma 1, gamma 2, 3 and 4, which is less than 10 dB, that is equal to 1 minus exponential of minus 0.1 whole to the power of 4. So already we discussed the same formula in the above equation, that is 1 minus exponential of minus gamma by tau whole power of m, where m equal to 4 here. In the above by using of above formula, we are supposed to use the same formula here, 1 minus exponential of 0.1 whole power of 4, that is equal to 8.2 into 10 to the power of minus 5. Are using selection diversity, we can be solved P gamma greater than 10 dB. So if it is less than 10 dB, if it is greater than 10 dB, 1 minus the above value. That means P of gamma greater than 10 dB is equal to 1 minus 8.5 into 10 to the power of minus 5, which is approximately equal to 0.9999. That is equal to approximately equal to 1. Choose the condition with the diversity. So if you are consider 4 symbols, 4 branches, which is less than 10 dB, the probability of occurrence is 8.2 to 10 to the power of minus 5. And if you are consider selection diversity with the probability is greater than 10 dB, that is equal to 0.9999, approximately equal to 1. But in the given problem, we have to also calculate the diversity without a diversity. Without diversity, we have to calculate the value of a probability of. Now, P of gamma 1 is less than or equal to 10 dB, that is 1 minus exponential of minus 0.1 whole power of 1, that is approximately equal to 0.095. So if it is greater than 10 dB, 1 minus the below value, 1 minus the above value, that is 1.0095, that is approximately equal to 0.905. So if you observe the analysis between with diversity and without diversity. So if you are consider selection of diversity with greater than 10 dB, that is approximately equal to 0.99 probability of error. But if you are consider with diversity, that is equal to 0.905. That is the main difference, the values which you by using diversity mechanism and without diversity mechanism. Now let us take some quiz on diversity techniques. Okay, so move bit number 1. Diversity requires a train of sequence. Option A is true and option B is false. Yes, option B is false. Explanation. Unlike equalization, diversity requires no training overhead sequence. A training sequence is not required by transmitter. Diversity is a powerful communication receiver technique that provides wireless link improving at relatively at low cost. So diversity requires there is no training sequence in the channel. So because it is more efficient method to remove the fading with a low cost. So coming to the bit number 2. Diversity decisions are made by the A. receivers, B. transmitters, C. channels, and fourth one is the adaptive algorithm. Yes, the answer is A. Completely made by the receiver. Explanation. In virtual in all applications, diversity decisions are made by the receiver and are unknown to the transmitter. Diversity exploits the random nature of a radio propagation by finding independent signal paths for the communication. Yes, diversity decisions are completely made by the receivers. It will not relate to the transmitters, channels, and which type of algorithm we are supposed to use. Coming to the bit number 3. Small scale faders are characterized by the which type of amplitudes? Fluctuation, which type of amplitude fluctuations? Like large, small, rapid, and finally slow. Yes, the answer is B, small amplitude fluctuations. Because of small scale fluctuations are characterized by the deep and random fluctuations. They occur as the mobile system moves over a distance of just a few wavelengths, like lies in between 0.5 wavelength to 6 wavelength. These fades are caused by multipath reflections from the surrounding in the vicinity of the mobile. So that's why small signal failures characterized by the small amplitude fluctuations only. It not produce large fluctuations, it not produce rapid fluctuations and slow fluctuations. So the answer is small. Now coming to the bit number 4. Dash is the used to prevent the deep fade for the rapidly varying channel. Option A, modulation. Option B, demodulation. Option C, microscopic diversity techniques. And option D, macroscopic diversity techniques. The answer is D, microscopic diversity technique. Why? Because what is the explanation? What is the reason it is microscopic diversity technique? In order to prevent deep fades from the occurring, microscopic diversity techniques can exploit the rapid changes of signal by selecting the best signal at all times. A receiver can mitigate small signal fading effects. So, microscopic diversity techniques are used to prevent deep fade for rapidly varying channels. So, that's why the answer is D. Now, move to the next bit. Large fading can be mitigated with the help of modulation, demodulation, macroscopic and microscopic diversity. It is similar to the previous bit. In the previous bit, we discussed rapid variant channel. Now we are using large scale fading channel. Yes, the answer is C. Large scaling panel mitigated with the macroscopic diversity technique. It is done by selecting a base station which is not shadowed when the other are. The mobile improve substantially the average to signal noise ratio. So that's why for large scale fading can be mitigated with the help of macro scale, for small scale with the help of micro scale. Now move to the next bit. Space diversity is also known as antenna diversity, B, time diversity, C, frequency diversity, and D, polarization diversity. Yes, the answer is antenna diversity. Space diversity is also known as antenna diversity. It is one of the popular form of diversity used in wireless communication like in MIMO and massive MIMO. Signals received from the spatial separate antennas on the mobile would have essentially uncorrelated envelopes of antenna separations. Here, OFDM plays an important role. In OFDM, orthogonal frequency division multiplexing use orthogonal carriers. Each carrier will having a orthogonality. Each carrier we can be called as a subcarrier. Each subcarrier having the orthogonality relation between them. So that's why the answer is antenna diversity. Now move to the bit number 7. Which of the following is not a category of space diversity technique? Option A, selective diversity. Option B, time diversity. Option C, feedback diversity. Option D, equal gain diversity. Yes, the option is time diversity. Why it is time diversity? Space diversity reception methods can be classified into the 4 categories. They are selection diversity, feedback diversity, maximum combined, and equal gain diversity. So, time diversity comes under, it is not a category of space diversity technique. Now, move to the bit number 8. In the selection of diversity, the gain of each diversity branch provides a different SNR. Yes, it may be true or false. What is it? True or false? Option B is completely false. Why? Because selection diversity use M demodulators to provide M diversity branches. Their gain is adjustable to provide the same average SNR for each branch. It is not different SNR, same average SNR for each branch. So that's why option answer is B. It provides same SNR for each and every branch, not a different SNR. And move to the next bit. Polarization diversity uses dash as the diversity element. Modulation index, carrier frequency, reflection coefficient, and last one is coherence time. A is the modulation index, P is the carrier frequency, and C is the reflection coefficient, and D is the coherence time. The answer is C, completely based upon reflection coefficient. Explanation. Decorrelation of the signal in each polarization is caused by multiple reflections in the channel between the mobile and the base station antenna. Reflection coefficient for each polarization is different, which results in the different amplitude and phases for each reflection. So that's why polarization diversity use reflection coefficient as a diversity element. We notify that the reflection coefficient theoretically lies in between -1 to +1, but practically the value of a reflection coefficient lies in between 0 to 1. How much of reflection that can be reflected back to the transmitter, that will be reflected back to the transmitter, the concentration we can be called as a reflection coefficient. Normally in field theory, it plays a crucial role to judge a waveguide. Similarly, in wireless communication also, the value of a reflection coefficient judge the efficiency of the channel. Why? Because if it is satisfy the maximum power transfer theorem, there is no reflections made by the receiver to transmitter. Why? Because maximum power will be delivered to the receiver side. If else, there is a possibility to existence reflection coefficient. So answer is C. Now, last bit. Which of the factor doesn't determine the correlation coefficient? Option A, polarization angle. Option B, cross polarization discrimination. Option C, offset angle from the main beam direction. Option D, coherence time. Yes, the answer is coherence time. Why it is coherence time? The correlation of coefficient is determined by the three factors. One is polarization angle between antennas, offset angle from the main beam direction to the diversity antenna, and next one is cross correlation discrimination. The correlation coefficient generally becomes higher as offset angle beams large. So that's why a factor, that is coherence time, doesn't determine the correlation coefficients. So that's why the answer is D. That's why the answer is D. With this mitigation of a degradation effects of the fading is completed. In this video, we covered the degradation effects of the fading. So to combat to distortion, combat in loss in SNR, and mitigation combat frequency, selective distortion. In that, decision feedback equalizer, maximum likelihood sequence estimator, and direct sequence spread spectrum, and finally frequency hopping spread spectrum, and of course orthogonal frequency and pilot sequence. And after that, we discuss mitigation to combat fast fading distortion, and after that, mitigation combat loss in SNR. In that, we discuss time diversity, frequency diversity, spread spectrum, frequency hopping spread spectrum, space diversity, and polarization diversity. And last, we have discussed about the diversity techniques. In the diversity techniques, we explain a problem with diversity and without diversity, and we calculate the value of a probability of error with diversity and without diversity. And we discuss a sum of bits which are related to the diversity scheme. I hope you understand the concept of diversity, technique, scheme. In the next chapter, we discuss about diversity combining techniques. What are the techniques in the diversity and modulation types of fading channels and variation of a mobile systems and the role of interleaver in the communication with a suitable example. Thank you.